So now, let's think about what x is as a function of time. If I pull my spring and my mass to the right, as in the first panel, and I let it go. It's on a frictionless surface, it has an ideal spring, it's all the assumptions that we're making, and I let it go, what's going to happen to the mass? Well, as we know, it's going to move past equilibrium, it's going to keep going, it has momentum. The force starts to turn and go the other way, so now it's pushing it back as it crosses the equilibrium position, because I'm compressing my spring. The force direction switches, it starts to slow down because there's a force opposed to the motion, and now it stops at some point, it compresses to its full maximum position, and now it starts to go the other way. The force is in the direction of motion until it hits its equilibrium position, and we go back and we cycle. So back and forth and back and forth. And we can think of some things that may go back and forth as a function of time, mathematically, that are going to help us determine what x, the position of my mass, is as a function of time. Okay, so now let's go ahead and think about how things look. We want the momentum principle. We want dp dt equals F net. Well, what are the forces that are acting on my spring? Now, let's do the free body diagram. We have the force, on my mass, so we'll give this a mass. We have the force of the Earth, or force on the mass due to the Earth. We have the force on the mass due to the table, we'll call it. Those are going to be in equilibrium because it's not moving in the y direction. And we also have, well, for any of these positions, we could write down a different force, but let's take the first one. We have the force on the mass due to the spring. Okay? And we could do the same here. The sign of this, the direction of this would flip. We have a balance of vertical forces, F mass table, F mass Earth. And now we have another force in the other direction, mass spring. And here it's just a balance of two forces. Right. Okay, so no horizontal forces. So we have all the things that we need to work with. We know the spring force minus k times x. These are going to be our starting points. And now we're going to think about, well, how do we start to define things? Well, in the momentum, we know that we have a velocity. So let's write down our velocity. The velocity, well, that's just the derivative, the first derivative of the position, dx dt. It's the change in position with respect to time. So that dp is now just equal to a mass times v, which is equal to mass dx dt. Okay, so that's pretty straightforward. So let's now think about how this all will come together. No, so this is just p. I'm sorry, not dp. P. Let's take the derivative of p. dp dt. Okay, so our mass is not changing. So we don't need to worry about that. That's a constant. So that can just step out. So now I have to take the derivative of the velocity. Well, that's going to be the mass times the derivative, d by dt, of dx dt. Okay, so I just pick up one more derivative of the position. So now dp dt is equal to the mass. Now I have two derivatives. d2 d squared x dt squared. The second derivative of the position times the mass is the change in momentum. Okay, so now we have dp dt. We know what it is. It's this. We know the net force. These two forces are balanced, so they cancel each other. So the net force acting on my spring in any position is given by the spring force, shockingly. So let's write that down. That momentum principle, dp dt, is F net, and F net is minus kx. That's easy. I could make x a vector, or I could decide to get rid of the vectors at this point. So let's just work in one dimension. We'll get rid of all of our vectors. Minus k sub s times x. What's dp dt? Well, now I've got a mass times d squared x dt. For a spring, this is the equation of the momentum principle. It is a differential equation, and so that means that I have a differential quantity on this side, perhaps, and a non-differential quantity on this side. I can now start to solve things, or think about how to solve this in an analytical way. That is, to come up with a solution that satisfies this equality. That's all I'm really doing, is balancing what's on this side to what's on this side. And that's what we're going to do now. We're actually going to come up with a solution that provides us how this is all going to look. So I'm going to get rid of all of this. I'm going to rewrite this. So here we go. Let's just get rid of that. So the mass times d squared x as a function of time, so this is x as a function of time, derivative squared, minus ks x. And if you want to be very technical about it, we can rewrite this as mass times d squared x as a function of time over dt squared is equal to minus ks x as a function of time. So what I need is something. If let's step back and actually look at this equation and figure out what we really need to do. Let's look at this side, the right-hand side of the equation. I have a function of time times some constant, and on this side of the equation, I need to have something that's equal to that, identically equal to that, if I take two derivatives of it. So I need a function, some function, where if I take two derivatives, of that function, mathematical function, I get the function back. I get the function I started with. That must be a crazy function. I take two derivatives of it, and in fact I need something where it's that function negative of that function. So I take a function, I don't know what it looks like yet. I take two derivatives of that function, take a first derivative, take the result of that first derivative, take the derivative again, and now I need that function that I started with to be equal to two derivatives of that function. What in the world could that function be? All right. Well, in a lot of ways, in mathematics, there are things that we do where it involves a little bit of a guess. So, let's assume a particular form for our function. So again, two derivatives, d squared dt must be equal to of something. Must be actually equal to negative of something. So this thing has to equal this thing. No messing around. It's got to equal that. Two derivatives of something has to equal the minus of something. Okay. Well, let's see. What do we get? It turns out there are a couple functions out there that do this. They're trigonometric functions. If I take a cosine of something, of position, let's just say I take a cosine. Let's take a cosine of something. I'm just going to put an omega here times t. This is just a cosine of anything as a function of time. Cosines and sines can have time dependence. So if I put time in here, a cosine function as a function of time, this is going to be cosine of something times time. That's the frequency, it turns out. Look like this kind of function, right? So it starts at 1. As I hit this point, this one's going to be, of course, 2 pi. Right? And so pi over 2 is here. If I take the first derivative of a cosine, what do I get? First derivative of cosine? Well, let's think about it. First derivative of cosine has to be, it's 0 here, it goes negative, so that must be a minus sine. So minus sine right? So there's a minus sign. This is minus sine omega t. Let's take another derivative. Let's take the derivative of minus sine. Minus sine, the first derivative of minus sine is, turns out, minus cosine. So, minus cosine omega t. I think we found our function. So let's look at that mathematically. I take a cosine function and take its derivative. D by dt of cosine omega t. That's equal to minus omega sine omega t. If I take this derivative, d by dt, of minus omega sine omega t, I get minus omega squared cosine omega t. Look at this. I started with a function, cosine omega t. Here's my question mark. Let's follow the question mark through. I take a derivative of it, first derivative, I get this. I stick this into another derivative. Sorry, let me get my parentheses right here. Yeah. There we go. Okay, so I start with my function. I take its first derivative, I get something. I take its derivative again. So this goes into here, I take another derivative. Look at this. I got back minus my thing. Ha! We figured it out, but I picked up a constant. But that's okay. Constants are all right. Look, I got constants. Now I have things to work with. So let's look at what we have. My x, I'm going to guess that my x of t better look like something like cosine something times t. This comes in because I want things to be correct mathematically. It's okay, it's just a constant times time. The first derivative, dx of t dt, well, that's going to be minus omega, this always comes out, sine omega t. dx squared t, d squared t, dt squared. Well, that's going to be the derivative of this, which is equal to the derivative of this. Yes? So that's got to be equal to minus omega squared. I pull another one out, that multiplies, cosine omega t. So there are my derivatives. First derivative, zeroth derivative, first derivative, second derivative. Now, here's this weird constant out here. Turns out that I have a weird constant here. If I divide by m, now I get m divides k sub s. And now I can write down the solution to my equation. All right, so let's go through that in all of its deep and dark glory. With a cosine and sine function, just rewrite everything. Get rid of my little graphic here. Let's think, this lecture is getting very long, so I'm going to stop it here and we'll start again. So this will be our starting point for the next one.